This book actually comes with 3D glasses if you had bought a hardcover of the book. So if you happen to have a 3D glasses and you use them looking at the screen, you should see something here with this crazy clock thing.
It's a shame I can't see in 3D.
You can't see in 3D?
I can't watch 3D movies.
Does anybody have any homework questions?
Like, with the glasses, it's just like, oh. Yeah, right? Things don't like come out. I think the Star Wars movie and stuff like
Okay, if nobody has any questions, we'll continue on with the section 2.4. The life lesson the author suggests here is to explore ideas systematically, investigate consequences, and formulate general principles. And we're doing that as we look at modular arithmetic. So modular arithmetic is when we take out multiples of a number, as we did with the clock. We took out multiples of 12 hours. And that's something where cyclical things are occurring. That is something that occurs naturally. For example, when we look at weeks are 7 days, and so when we're counting weeks, we would take out multiples of 7. We're going to see some other examples of using the modular arithmetic. I guess I'll show you right away in our textbook some examples suggested by the author. So what your author calls crazy clock arithmetic or modular arithmetic helps us find errors in grocery prices, or checking accounts, UPS package deliveries, airline tickets, and driver's license numbers. So we'll see a couple of those examples right in class. So modular arithmetic is a useful skill. Let's go ahead and make sure you know how to do modular arithmetic. That is one of the things that you'll see on your quiz, is some modular arithmetic problems. So if we look at 415 hours from now, and we're trying to figure out what time it will be, we're doing modular arithmetic. We're taking out multiples of 12. We took the 415, and I think this might be one we did in class Monday. We divide by 12. And the whole number tells us how many multiples of 12 we're able to remove. So 34 multiples of 12. So 12 times 34, how many hours is that? 408. So we subtract away 34 multiples of 12, or 408, and we have a remainder of 7. That means 415 hours from now, the clock will be 7 hours ahead. So our clock says 8:30, 7 hours ahead. You could just count those off. So that'd be 3:30. Well, what we say in math is we say that 415 is equivalent to, and we use the 3 bars to mean that it's not equal, but it's equivalent to 7 mod 12. So this clock arithmetic we've been working on is mod 12 arithmetic. It means we took out multiples of 12, and when we did that, we got 7. Yeah.
On the quiz, like, do we have to write 415 is equivalent to 7 mod 12?
So on the quiz, what you'll see is a little underline here. Here, let's do an example like you'd see on the quiz. and you have to fill in the underline, okay? So we have to figure out what is 25 equivalent to in modular 7. So in mod 7, we're taking away multiples of 7. So you would work on that. You'd say, okay, I'm going to take the 25 and divide by 7. And some of you can do that in your head.
Wouldn't it be 4 mod 7?
You're ahead of me. Yes, good job. It is 4 because you take away 21, 3 multiples of 7, and you have 4. So the remainder is the number that you're equivalent to. So that's what you'll see on the quiz. You'll see these little underline blanks that you need to fill in. So we're going to practice that for a bit this morning and make sure everybody knows how to do this so that you're set for the quiz. And then we'll use it for an application. So we'll stick with mod 7 for a bit. Here I have 210 mod 7. Yes?
0.
It is 0. Good. Because 210 divided by 7 goes evenly. There's no remainder at all.
The reason why I said 30 because 7 divided by times 3 is 21, and then you add the 0 because it has an extra 0 on it. So.
Good. I'm glad you can do that in your head. Always helpful. Here's another one. 421 is equivalent to what? Mod 7. So 421 does not divide evenly by 7. You get 60 point something, but 60 times 7 is 420. And so when we subtract, there's a remainder of 1. So 421 is 1 mod 7. How about we do some mod 4? So if you know your multiplication table, some of these you can do in your head, right? Anyone know this one? It is 1. Good. Good. Because 25 divided by 4 is 6 point something. Because 6 times 4 is 24. And when you subtract, you get that remainder of 1. Let's do a mod 8.
It'd also be 1.
Good. Yep, that would also be 1 because you have 9 divided by 8. Go in there 1 time, and a remainder of 1. Okay, so I'm going to put out 4 different examples and walk around and see how you're doing so that you can make sure you know how. And raise your hand if you're stuck. I don't want you to be stuck on questions that you can might see on the quiz. So how about I do a 15 mod 4, 327 mod 4, another big number, 416 mod 8, and 36 mod 4. Okay, so we work on that and I'll come around. And students at home, you can check your work in a minute. And if you're stuck, just raise your hand, please.
Same here. It's like,
Yeah, since it's seven, oh, it's mod 4. I put mod 8 on my paper. So this one you did the 4. Put a 16 instead of 15. So you're gonna go yeah, 320. Oh, this is 327, you can go one more. So you can go 81. Anybody need help? Raise your hand. Your answer should always be smaller than this number. Your answer should always be smaller than this number. Okay? Because your remainder will always be smaller than these numbers. So 15 divided by 4 is 3. Remainder 3, so 3 from the remainder. 327 divided by 4, that'd be 81. Remainder 3, so 3 for that one also. 416 divided by 8, that goes evenly. No remainder, so 0. And 36 divided by 4, 9. Good. Yeah, I thought I had mod 8 up there, so I kept wondering why everybody was getting 0, but it's because I had a 4 and not an 8. So it's just your remainder. Let's go ahead then and see an application of this. So there's several applications. If you go on and read in the next section of your textbook, you can see how the modular arithmetic is used for cryptology. We're going to use it for looking at UPC codes, universal product codes. So you see you have these numbers down here? This last number is a check digit, and then there's a pattern of multiplying we do, and we want to pick out a check digit after that, or the person who manufactured this did, so that they can know when you call in and you have a question, or you're sending UPC codes for some purpose, they can know if you are reading the correct number to them over the phone, for example, or if you sent the correct universal product code in. So they can tell if this universal product code is just off by one number, the check digit will let them know. Okay. So let's go ahead and write that universal product code down. After I take it off screen so you can't see it. Here, I'll put it back in a minute. Okay, so this is a box of Kleenex. Some of the digits will help the manufacturer know, well, who manufactured it. So put plenty of space here because you're going to need to do arithmetic with these. So this last digit, 0, is the check digit. So I just wrote them down with lots of space. So it's 036 036 000 21400. So what the pattern is to take each of these digits and multiply by 3 or 1 in an alternating pattern. So the first digit times 3, the next digit times 1, the next digit by 3, the next one by 1, and so on. Not the check digit though. The check digit doesn't get multiplied. So after we do this multiplying, we're going to add all these numbers up. So 3 times 0 is 0, 3 times 1 is 3, 3 times 6 is 18, 1 times 0 is 0, 3 times 0 is 0, 1 times 0 0. 3 times 6 is 2. 1 times 1 is 1. 3 times 4 is 12. 1 times 0 is 0. 3 times 0 is 0. So we do this pattern 3 1 3 1 3 1 3 1, and then the check digit brings the sum to be equivalent to 0 mod 10. So once we do this little pattern of multiplying times 3 times 1 times 3 times 1 times 3 times 1 times 3 times 1, the check digit will bring this total to be 0 mod 10. So that's how the check digit is chosen. So the UPC code helps the people know what plant it comes from, what company it comes from, whatever they want to encode in there. But then the check digit is used so that if you're trying to compare a UPC code, you know that, okay, you just have not written this down correctly if it doesn't come out right. So let's check. Did anybody add all those up? What did you get?
I got 40.
40? Anybody else get 40? I didn't add them up yet. Nobody else added them up? You got 40 also? Okay. Okay. So 40 is equivalent to 0 mod 10, and that's why the check digit is 0, because the sum is already equivalent to 40 mod 10, because 40 divided by 10 is, of course, 4 with no remainder. Let's try a different one. Does somebody want to give me a universal barcode? Do you a universal product code? Does anybody have one? Anybody have something with that? Not your beverage, but your food might work. Beverages,
Oh, this is gum.
yeah, beverages don't usually work. We'll try one. Okay, so we'll try this gum. Okay, can you please read it off?
That's so weird.
There
Oh,
should-
it got cut off.
Oh.
Never mind. Never mind. False alarm.
Yes, what do you have?
I have this water bottle here.
I don't know. Beverages don't usually work.
It's like this.
Oh, a water bottle. Okay, that might work. Okay, let's try it.
810-922-034-843.
Okay, so yours is too long for this. There's a different method then. Okay, so yours is a longer one than we're using. We need a 9 digits, or is it 10? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh no, I'm sorry, you're correct. You're fine. This one had that same number. Okay, what was it?
810-922-034-843.
Okay, so the 3 should be the check digit. So 810-922-034-843. So we multiply times 3, times 1, 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 times 3. Okay, and we add these up. And then the last number 3 should make sure that we end up with getting a 0 mod 10. So let's check. So we're doing the multiplying. Now we're going to add. Yeah, so these all add up to be 77, and we need it to come out to be 0 mod 10. You know, everything that's equivalent to 0 mod 10 ends in a 0, right? Okay, because we're looking at multiples of 10. So if it's evenly divisible by 10, which is what we need, then you have to end at a 0. So that's why they picked 3, because now we have 80, which is equivalent to 0 mod 10. So in other words, you need this multiplying scheme to come out to end in a 0, and that's how the check digit's chosen. Anybody have another one you want to try? Any UPC codes there? I brought some more if you didn't. Here, let's check. Here's some chalk. Okay, this chalk we have 0, 7, 2, 0, 6, 7, 3, 1, 1, 4, 4, and the check digit there is a 3. So on a quiz, I'd not give you the check digit, and I'd ask you to find it. Okay, so we'll try that on another one here in a minute. Now you got to remember what you start with. You start with multiplying by 3. So that's probably something you would put on your 3x5 card. The scheme here that you multiply by 3 by 1 by 3 by 1 by 3 by 1. The last one, you can think of it as multiplied by 1 if you want to, but of course it's an extra number to check. So 3 times 0 is 0, 7 times 1 is 7, 2 times 3 is 6, 1 times 0 is 0, 3 times 6 is 18, 1 times 7 is 7, 3 times 3 is 9. Oh, that's weird. Why did that happen? Anybody get that added up yet? 67? Thank you. And so that gives a check digit of 3 necessary to get us to 70. Because 70 is equivalent to 0 mod 10. So this time I won't tell you the check digit. This is a UPC code from my chenille sticks, fuzzy sticks from the kit that you purchased. I bought mine in parts. Okay, so here we go. 7, 6, 5, 9, 4, 0, 1, 8, 2, 3, 2, and then find this. Okay, find the check digit. Make sure I wrote it down right. Okay. what did you get? What?
1.
Good, 1. So your check digit is 1. And how come? What was this sum?
89.
Good. So you need one more to bring you up to 90. You have to end in a 0 to be equivalent. Your digit has to end in a 0 to be equivalent to 0 mod 10. So that's how the check digit works. In your homework, you'll have a few problems that ask you to find some of these numbers instead, and you'll know the check digits. So then it takes a little more work, because then you have to think, well, what do I have to multiply? Am I multiplying by 3 or 1, and so on. So you'll have to think a little backwards on that. And you can certainly ask me in class if you're stuck.
What if you already did the assignment?
That's fine. If you already did the assignment, that's fine. Hopefully you got it right.
Most of it.
Okay, good. Any other questions? Okay. Another use these check digits are used for are for banking. The method that's used in banking is a little different, a little harder. So the method in banking is to check routing numbers and to tell if either two numbers are transposed or just wrong. So here I brought a check. This was a rebate check. And we're checking the routing number here. The first numbers up to this colon are the routing number. The 0, 9, 1, 9, 8, 1, 8, 1, and then the 1 is a check digit. So we still want to get to 0 mod 10 with the check digit. But the pattern here is more complicated. It's 7, 3, 9, 7, 3, 9. Wait, did I miss a digit? Let's see. 1, 2, 3, 4, 5, 6, 7. There's 2 ones? Oh, thank you.
Oh, there's 2 ones after the 8. Yeah, it's like 9, 1, 8. Oh shoot, right? 9, 8, 1, 8, 1, 1.
0, 9, 1. Oh, I see right in here. Okay, thanks.
There's a.
Like that, right?
No, there's a one after that one. 1, then another 8.
Okay.
Then 2 ones.
Right, thank you. Okay, so this should work. The pattern is 739, 739. This is why they have computers do this, right? So this should come out to 0 mod 10. So 739, 739, 739. So what do we get? Yeah, so that comes out to 200. So the bank routing numbers use a different code that's a little heftier, can catch a little better transposition of numbers. So when you file your taxes electronically and you're looking for that refund and you had to type in your routing number, it should kick it back if it has an incorrect routing number. The one that you need to know though is the one here. Okay, you need to know this pattern and how to find the check digit. Okay, so know how to find the check digit. For just the UPC. You don't need to know how to find the check digit for the bank check. But you might see some homework about that on the computer about the bank check, and that I wanted to make sure I showed you one of those. Does anybody want to see another check one? Not a check digit, but a check. And then the class activity for today was this one that we did first with a Kleenex box. So the first one we did was the Kleenex box, and that's the class activity for today. So you can take a photo of that and upload it by Sunday night, please.
The banking?
The Kleenex one. Oh, do you have a question about the banking one?
No, which one is our class activity?
The Kleenex one, which was the very first one we did.
Can you be any tissue box?
Well, you could do it again with a different tissue box if you want, or you can take a picture of the one we did together in class, and then you don't have to do it again. Yeah. Any other questions? We are going to go on to section 2.6. We are skipping 2.5. You can look at 2.5 on your own if you want. It's the encryption, and it's very interesting, but it also takes a lot of time and a lot of thought, and so we're going to move ahead to 2.6. We won't have time to do the whole book, so I picked out things that I thought were either fundamental or more interesting. And not too hard, because there's some things that are interesting that are just hard. Okay, 2.6. We're looking at rational numbers. Your author opens with a question we will be considering later. How can we prove that all numbers are rational? In other words, all numbers are fractions. So there were several types of numbers that I said you'll need to learn the names of, and one of those sets of numbers are rational numbers, and those are numbers that can be written as fractions. So rational numbers are able to be written as fractions. It froze up. Let me unfreeze this. Okay. So rational numbers can be written as fractions, but we have a little more formal definition. They can be written as a divided by b, where b is not 0, because division by 0 is undefined. And a and b are integers. So that brings up another set of numbers, integers. So rational numbers, do you see the word ratio in the rational? That helps you think about what those are. Okay, ratio, rational, ratios. Ratios are fractions. Okay. So rational numbers can be written as fractions, where a and b are integers and b is not 0. So that brings up the integers. We haven't looked at integers as a group yet. Does anybody know what integers are? Integers have no fractional portion, but they're more than the natural numbers. Remember, the natural numbers where 1, 2, 3, 4, and so on. The integers include 0 and the opposites of the natural numbers, the negatives. So we have to put dot, dot, dot to the left and dot, dot, dot to the right because we keep counting forward and backwards with the integers. Before we look at this section, we're going to do a little bit of algebra. So we're going to consider solving an equation. So we're going to solve the equation 2x plus 3 equals 5. Solving means to find the value for x that makes this true. And some of you can just think it out in your head, and that's fine. Here we're going to remember that whatever you do to one side of the equation, do to the other. So whatever you do to one side of the equation, do to the other. And that will keep your equation true. The equal sign means that both sides are equal. It's like a balance scale. Have any of you used a balance scale, maybe in physics or science? And you have to put the same weight on both sides. So here you could say both sides are like a 5. So the fulcrum's like the equal sign, and both sides are the same weight. So if we take away 3 from the left, and we take away 3 from the right, the scale is still equal. They're still both at 2. So if both sides start out equal, and you take away 3 from both sides remain equal. Then we go ahead and divide out the 2, and x is 1. So x is the number that makes the equation true. You see you now have 2 times 1 plus 3 equals 5. You can check that out. 2 times 1 is 2, and you add 3 and you get 5. So that checks out. So whatever you do to one side of the equation, you do to the other when you're solving equations. We're also going to look a little bit at square roots. So the square root of 4, what would that be? Anyone know what that is? The square root of 4 is 2 because 2 times 2 equals 4. So when we look at a square root, we're looking for the number that you multiply times itself to get this value 4 under the square root symbol. That's called the radicand. So if we have the square root of 25, what would that be? 5, yes, because 5 times 5 is 25. Now if you have the square root of 7, you would just leave it. Mathematicians leave the square root of 7 as the square root of 7 because that's the exact value. There's a section on in your textbook that we don't get to that shows if you start rounding things off how far your answer can differ from somebody else's just by doing repeated operations where you're rounded off differently. So we like the square root of 7, even though your calculator will say, let's see what it says. Square root of 7, 2.646 about. So it's approximately 2.646 when you say the square root of 7. However, if you take 2.646 times 2.646, you do not get exactly 7. You get 7.001316. So mathematicians like to keep everything exact as long as you can, and you can as long as you name what the square root of 7 is by calling it the square root of 7 instead of rounding it off. The approximation is sometimes used, this little symbol right here, this little squiggly equals. So that's what that little squiggly equals means. It means approximately. Let's look at fractions. We put everything everybody loves in one section of review, including fractions. So for many of you, this review is just that, it's review. So I appreciate you being patient. Some people don't remember this. There's no math prerequisite here, so we have to review these things, okay? So if you take one pizza and cut it in half, then the 2 in the bottom here shows that you cut the one pizza into 2 parts, and the 1 in the top means you have one of those 2 parts and one of those 2 parts. So if you have a 1/4, that means that you cut the one pizza into 4 parts, and the 1 on the top means one of those 4 parts right there. Now if you wanted to add halves and fourths, then they're not the same size. So to get them to be the same size, you take your 1/2 and you cut it in halves. Okay, so you have 1/2 and 1/2, and then you cut those in half. So the 1/2 of the 1/2 is 1/4. The way we do that with algebra is to take the 1/2 and multiply it by 2/2. So when you multiply by 2/2, that divides each of those pieces into smaller pieces, into fourths. So now you have 2/4, because you have the 2 times the 1 on the top and the 2 times 2 on the bottom. And you have 3/4. So 1/2 plus 1/4 is the same as 2/4 plus 1/4, or 3/4. Now the 2/4, rather the 2/2 is the same as 1. And that's why you can multiply by half and not have any change in your value, because 2/2 is just 1. We're going to go the other way with fractions a bit. We're going to reduce. So if you have a fraction like 3/6 and you want to reduce it, you would think of that as a 1 times 3 on the top and a 2 times 3 in the bottom, and then you divide out the 3/3, because the 3/3 is just a 1. See if I can squeeze a 1 in there, okay? So if you have 35/40, you can see those are both multiples of 5, and you would take a 5 out. So 5 times 7 and 5 times 8, you get 7/8. So fractions are reduced when you've gotten all these multiples out that are common, and you can write them in their smallest, the smallest numbers that you can. So let's take a look at some numbers, and you can tell me which ones are rational. Let's change that to -4/9 so it's reduced, okay. So we have 1, 5, 0.7, 3/5, 0, -2, and 4/9. At your desk, go ahead and circle the rational ones. Circle the rational numbers. So remember the definition we just talked about. They're able to be written as fractions. Which ones did you circle? Yes.
I circle 1, 5, -2, 0, 3/5, -4/9.
So you circled everything but 0.7? Okay, did anybody circle 0.7?
And you can, because like, if you put it into a fraction, it's 7/10.
That's right, yeah. So this one you can circle too. So all of those were rational numbers because you can take any decimal that ends like that and write it as a fraction. You just have to put the correct power of 10 underneath it. Well, I think we will stop there because the other class usually has questions, so that way we won't be too hung up. So we'll pick up here with some more work on rational numbers. I'll see you on Friday.
Y'all are only gonna have one class on Friday.
Isn't that nice?
It is nice.
I like that.
Because today I only have this is German, Thursday I only have one class, and then Friday I only have math because my German teacher's gonna be at a conference. So
At a conference.
yeah.